Hello, everybody. Welcome to part 2 of geometry, where we'll hopefully have the time to finish all the AMCA geometry questions. Okay, so I believe this was the last problem we did last time. So I believe we should start with this problem here. Okay, so, and don't forget Benjamin's here, so if you have any questions, feel free to message him. Okay, so in triangle ABC, point D divides side AC so that AD to DC is equal to 1 to 2. Let E be the midpoint of BD, and let F be the point of intersection of line BC and line AE. Given that the area of triangle ABC is 360, what is the area of triangle EBF? This class is 1 hour long, if that's what you're talking about. So does anybody have any answers except for one person who sent their answer? Okay, so I'll start setting up the problem for you guys. So basically, they're saying that AD to DC is 1 to 2. So that means the length of DC is double the length of AD. So for example, if AD has length x, then DC has length 2x. And E is the midpoint of BD, which means these two lengths are equal. And F is the intersection of BC and line AE. And we're told that the area of the entire figure is 360. And they're asking for the area of EBF, which is this triangle. So try to solve this problem with ratios of triangle areas. So for example, you know that since triangles ABD and DBC share the same height, the ratio of their areas is the same as the ratio of their bases. And there's actually another technique to solve problems like this that you can use called mass points. So I don't know how many of you heard of mass points, but if you guys want, we can try that. Okay, so we have several people asking to do mass points, so let's just try that. So to go over the basics, just picture, for example, if you go to a playground or a park, you might have a seesaw, right? Like, for example, here's the base of the seesaw, and here's your seesaw, right? So basically, the idea of this is that if you use mass points in a figure with lots of triangles like this one, then it's kind of like playing a seesaw. So for example, each point in this figure has a certain weight. And their weights are related in how the side lengths of this triangle are related. So for example, if DC here has twice the length of AD, then that means that point A has twice the weight of point C. So that's basically how mass points works. So since DC is twice of AD, then if point A has a weight of 2, then point C would have a weight of 1. So does everybody understand that? Okay, so they also tell you that BE is equal to ED. And since those two lengths are equal, we know that point B and point D have equal weights. So an interesting thing you can do here is to get the weight of point D, you can just add the weights of point A and point C. So 2 plus 1 is 3, which means that point D here has a weight of 3. And since BE is equal to ED, B and D have the same weight. So the weight of B is also 3. And that means the weight of point E is 3 plus 3, since B, E, D are all on the same line. And that is equal to 6. And if E is 6 and A here is 2, then that means point F must have a weight of 6 minus 2, which is 4. And you know that it works out because 4 here is equal to 3 plus 1. So what we've done is we've assigned every single point in this figure with a weight. And what this gives us is some new information. And one of these pieces of information is that the ratio of BF to FC is 1 to 3. So does everybody follow that so far? Okay, good. So if you guys have this information, can you try to continue solving the problem? Don't forget that the area of the whole thing is 360. Well, there are multiple triangles in this figure that have the same height. So like, for example, triangle ABD and DBC have the same height. Triangles AFC and AFB have the same height. Triangles BFE and BEA also have the same height. So in all those cases, the ratio of the two triangles' areas is just equal to the ratio of their bases. I'm not sure what you mean when you say AE has a ratio of 1 to 3. Oh, you mean the ratio of the weight values, Ian. Um, well, yes, technically they have a weight ratio of 1 to 3, but that doesn't really tell you anything unless there are lines that you can apply that to. So, like, for example, the weight of certain points won't give you any information to solve the problem. What you need to do is, for example, if you have 3 points in a line, and you know the weight of this point is x, and you know the weight of this point is y, then that tells you that the ratio of this length to this length is y to x. So try to look at it in terms of the ratios of like side lengths, not really the ratio of weights. Okay, so basically, I'm just gonna go ahead and solve the problem here. So there are a few types of ways you could do this problem, but the way I'm going to show you is just one of them. Okay, so we know that, okay, someone's asking me to wait. Okay, sure. Okay, let's go ahead. The way I'm going to show you is just one of the ways you could solve this with mass points. So we know that the ratio of BF to FC is 1 to 3. So if we go back to the original statement, they tell us that the area is 360. So if we split 360 into 4 parts, then we get 90 each, which means that the area of triangle ABF to the area of triangle AFC is equal to 1 to 3, right? Because their base lengths are 1 to 3, and they have the exact same height. So that means that in order for them to add up to 360, the area of triangle ABF must equal 90, and the area of triangle AFC should be equal to 270. Okay, so now we know that the area of triangle ABF is 90. So that's what we need. And notice that each time I do this, we're going to kind of narrow down our area until we just get to the area of triangle EBF. So we have our number 90, and now let's try to find the ratio of FE to EA. So because A has a weight of 2 and F has a weight of 4, that means the length of FE to EA is 2 to 4, which is 1 to 2. So that means that because they have the same height, the area of triangle BEF to the area of triangle BEA is equal to 1 to 2, right? And we know that the area of both of them added together is 90. So if we try to split 90 into 3 equal parts, we would get 30. And which would mean that the area of triangle BEF would be 30, since it's 1/3 of that 90. So hence our answer is B. So basically what we've been trying to do is we've used mass points in order to find the ratio of all the different side lengths in the figure. And using that, we've kind of narrowed our area down to what they were looking for. So first we had 360. Okay, that's not hence. Okay, sure. Okay, so first we had 360, And then we narrowed it down to 90. And then we narrowed it down again to 30. And that was the answer. So this was kind of a tricky problem. And it's also number 24, so it's a later problem. And if you have any questions, you can message Benjamin. But I'm going to, for the interest of time, go on to the next problem. Okay, so in triangle ABC, a point E is on AB with AE is equal to 1 and EB is equal to 2. Point D is on AC so that DE is parallel to BC, and point F is on BC so that EF is parallel to AC. What is the ratio of the area of CDEF to the area of triangle ABC? So I'm gonna just start labeling. So we have that's 1, that's 2. Okay, so let's go ahead and get started. So they're asking for the ratio of CDEF to ABC, and ABC is the whole thing, of course. So CDEF is just going to be this parallelogram right here. So if we notice, we can, because of these parallel lines, we can kind of use similar triangles. So we know that triangle ADE is similar to triangle ACB, for example. So if something that you guys should memorize is that if two triangles are similar, then the ratio of their areas is equal to the ratio of their side lengths, but squared. So because AE to EB is equal to, oh sorry, AE to, oh no. Okay, so AE to AB is equal to 1 to 3. Then that means that the area of triangle ADE to the area of triangle ACB is equal to 1 to 3 squared, which is 1 to 9. So similarly, you can do this with the other triangle. So because you know that BE to BA is equal to 2 to 3, then you know the triangle BEF to the area of triangle BAC is equal to 2 to 3 squared, which is 4 to 9. So we know that the areas highlighted in green here combined already take up 5 to 9 of the total. Because if we add these two up, we get 5 to 9. So since we want the yellow area, which is the opposite of that, 1 minus 5 over 9 is 4 over 9, which means the yellow area is 4/9 of the entire triangle, which should be A. Okay, onward. In square ABCE, AF is equal to 2 times FE and CD is equal to 2 times DE. What is the ratio of the area of triangle BFD to the area of square ABCE? Okay, so let's get started. So because they're asking for a ratio of areas, that means that we can set any numbers we want and we'll still get the same answer. So just for the sake of it, let's set EF to be 2. And that means that AF is going to be 4, which means the side length of our square is 6. So because CD is equal to 2 times DE, that means that this is 2 and this is also 4. So they're asking for the ratio of BFD. And BFD is just going to be this triangle here to the area of ABCE, which is just the entire square. So we already know off the bat that the area of the square is 6 times 6, which is 36. So that goes on the bottom. And to get BFD, what we can do is we can take the total area of the square and minus the 3 other triangles that are white. So 36 minus, so the area of FED is going to be 1/2 times 2 times 2. And the area of ABF is going to be 1/2 times, because this is 6, 4 times 6. And the area of BCD is also 1/2 times 4 times 6. So we can actually just double our last term. Instead of multiplying it by 1/2, we'll just multiply it by 1. So it just becomes 4 times 6. So if we simplify this, we get 36 minus 2 minus 24 over 36. And that gives us 5 over 18, which is C. Okay, so onward. Point E is the midpoint of side CD in square ABCD, and BE meets diagonal AC at F. The area of quadrilateral AFED is 45. What is the area of ABCD? Yes, this is a square. So it says right here that it's square ABCD. Oh, are you asking if the answer is a square or if the actual shape is a square? Yeah, the shape is a square. Okay, so let's go ahead and get started. So they tell us that AFED is 45. So this right here is 45. And E is the midpoint. Okay, so the best thing to do in this problem is, let's just say that the area of EFC we set to X, right? So now we can try to write all the other areas in terms of X. And because AB and EC are parallel, we know that ABF is similar to FEC. Or, yeah, those two triangles are similar. And because the ratio of their side lengths is 2 to 1, since AB is twice of EC, that means that the ratio of their areas is 4 to 1, since it's 2 to 1 squared. So if that's X, then we can say that this up here is 4X. And let's just try to come up with some equations. So we know that 45 plus X makes up half the square, since ADC is half the square. So 45 plus X is equal to half times square. And we also know that trapezoid ABED takes up 3/4 of the square. So then we know that 45 plus 4X is equal to 3/4 times square. Okay, so we know that the trapezoid takes up 3/4 because there's a few ways you could do it. The easiest way is just to notice that if you split the square in half down the middle, we have on the left side exactly 1/2 of the square right here, and in the other half of the square, exactly half of it is part of the trapezoid. So it's 1/2 plus 1/2 of a half, which is 3/4. That would be the simplest way. Okay, so essentially we have two equations set up here. And if we just isolate square and set it equal to itself, we get that we get that 90 plus 2x is equal to 180 plus 16x over 3. So if you just try to solve for x and square, then you should be able to find, since they're asking for the area of the square, that the area of the square is b, which is 108. Do you guys want me to actually go through the algebra? Okay, it looks like we have more yeses than nos, so okay then. Okay, so if we multiply both sides of this equation by 3, then we're going to get that 270 plus 6x equals 180 plus 16x, and that gives us 90 equals to 10x, which means x is equal to 9. So we can just pick any of the original equations to plug it into. So for example, if we plug it into the first, then we're going to get the 45 plus 9, which is equal to 54, is equal to half of the square, which means that the square is 54 times 2, which is equal to 108. Okay, so basically what I did in this equation here is I set square equal to itself. So in the first equation over here, I multiplied both sides by 2 to get 90 plus 2x equals square. So that's where this side comes from. And in the second equation, I multiplied both sides by 4 over 3 to get this. Okay, so let's move on. An equilateral triangle and a regular hexagon have equal perimeters. If the triangle's area is 4, what is the area of the hexagon? Okay, so we have an equilateral triangle and a regular hexagon with equal perimeters. So let's call both of their perimeters equal to, for example, 6x. That would mean that each side of the triangle has a length of 2x, and each side length of the hexagon is equal to x. So we're told that the triangle's area is 4. And we're asked for the area of the hexagon. So if you try to take apart a hexagon, you'll notice that a hexagon is just 6 smaller equilateral triangles, right? And each of those tinier equilateral triangles has a side length of x, and our triangle here has a side length of 2x. So that means that those two triangles are similar with a side ratio of 1 to 2. So that means that their area ratio is 1 to 2 squared, which is 1 to 4. And so that actually means that since the area of the bigger one is 4, the area of the smaller triangle must be 1. So each of these small equilateral triangles has an area of 1. And since there are 6 of them, that means the answer is C, 6. Okay, so let me explain it again. So we know that for two similar triangles, the ratio of their areas is the ratio of their side length squared, right? So this triangle colored in green and this other triangle colored in green are similar because all equilateral triangles are similar to each other, right? Okay, so each side of this bigger triangle is twice the side of the other. So the side length ratio is 2 to 1. So if you square that to get the area ratio, that's 4 to 1, which means that the bigger triangle is 4 times the area of the smaller one. And since the bigger triangle has an area of 4, that means the smaller triangle has an area of 1. So since there are 6 of these smaller triangles, the total area is 6. Okay, cool. So we are moving on. Okay, quadrilateral ABCD is a trapezoid. AD is equal to 15, AB is equal to 50, BC is equal to 20, and the altitude is 12. What is the area of the trapezoid? So the altitude means the height. So basically, this length right here is 12. And there's a right angle here. So basically the distance between parallel lines AB and CD. Okay, so I'm gonna get started. So we know that basically the altitude here is going to be the same no matter where we draw it. So let's just draw an altitude here and draw another one here. So we know that this is 12 and this is also 12. It's all 12. So this triangle I'm highlighting in yellow here is a right triangle, and we know 2 of the side lengths. So if we use the Pythagorean theorem, we can get the third one. And that is going to be, this is basically a 3, 4, 5 triangle, except every side is multiplied by 3. So that means this side is going to be 9. And similarly, this triangle I'm highlighting in yellow is also a right triangle, and we know 2 of the side lengths. So if we use Pythagorean theorem, then this triangle is basically a 3, 4, 5 triangle, except every single side length is multiplied by 4. So that means that this here is 16. So we're given that AB is 50. So basically what this trapezoid is is basically two small right triangles plus a big rectangle in the middle. So if you add up the individual areas, 1/2 times 9 times 12 plus 1/2 times 12 times 16 plus the big rectangle in the middle, which is 50 times 12, you should be able to get 750, which is D. Yeah, you could also use the area of the trapezoid formula. So that would be 1/2 times the total height, which is 12, times the sum of the bases, which is 50 on the top, plus on the bottom is 9 plus 50 plus 16, and that would give the same answer. Okay, so moving on. Rectangle ABCD has side CD is equal to 3 and DA equals 5. A circle of radius 1 is centered at A, a circle of radius 2 is centered at B, and a circle of radius 3 is centered at C. Which of the following is closest to the area of the region inside the rectangle but outside all three circles? Okay, so basically to solve this problem, we'll take the area of the rectangle and subtract the area of the quarter circles, which is this quarter circle, and this quarter circle. So the area of the rectangle is 15, and the area of the circle is pi r squared. So for circle A, it's 1/4 times pi times 1 squared. For circle B, it's going to be 1/4 times pi times 2 squared. And for circle C, it's going to be 1/4 times pi times 3 squared. And basically, we're going to be asked to estimate what this value is. So do you guys want me to go through this or just tell you the answer and move on? Okay, so I'm just going to quickly go through. Okay, so 15 minus, so basically we can factor out a 1/4 pi, so minus pi over 4 times 1 squared plus 2 squared plus 3 squared. So 1 squared plus 2 squared plus 3 squared gives us that minus pi over 4 times 9 plus 4, which is 13, plus 1 is 14. And we can cancel out something to get 7 pi over 2. So basically we're asked to estimate 15 minus 7 pi over 2. And pi, if you just approximate it to 3.14 should be enough. So 7 times 3.14 is just going to be 21.8 something-ish. Divided by 2 is just going to be 10 point something-ish. And 15 minus 10 point something-ish should give you approximately around 4, since it's on the higher end of that. Well, I'm sure if you can if you actually like plug it in and calculate it, you can get to close enough to 4 that you'll realize that the answer is B in the real test. But okay, so moving on. If you have any questions, you can type in the chat. I would prefer not to mute anyone because I have no idea who I'm unmuting. And yeah. Okay, so we might have time for 1 or 2 more questions. So let's just do this one. A decorative window is made up of a rectangle with semicircles at either end. The ratio of AD to AB is 3 to 2, and AB is 30 inches. What is the ratio of the area of the rectangle to the combined areas of the semicircles? Okay, so we're given that AD over AB is equal to 3 over 2. And we're also given that AB is equal to 30. So if you multiply both the top and this bottom of this fraction by 15, you'll be able to get a denominator of 30 while also getting a numerator of 45, which means that AD here is 45 and AB is 30. Okay, so that means that the radius of each of these semicircles is 15. And the combined area of 2 semicircles is just one normal circle, which has an area of pi times 15 squared. And the area of the rectangle is 30 times 45. So if we take a ratio here, then we can cancel out both 15s. And this would give us 2, and this would give us 3. So 2 times 3 over pi, which is 6 to pi, which is C. So that was a pretty easy one. Let's just see if we can do one more question before time is up. A semicircle is inscribed in an isosceles triangle with base 16 and height 15, so that the diameter of the semicircle is contained in the base of the triangle as shown. What is the radius of the semicircle? We're just going to quickly finish up this problem, and it'll be our last problem today. Okay, so they tell us that the diameter of the semicircle is on the base, which means that the center of the semicircle must be the midpoint of the base. Oh, sorry, we just went back one. Okay, there we go. Okay, so as I was saying, the midpoint of this base is going to be the center of the semicircle. And when you see a problem where you have tangent lines to a circle or an arc, then you kind of have to connect to the tangent point. And if you connect to the tangent point on either side, then you always meet at right angles. So they tell us that the height is 15. So that length right there is 15. And the base here is 8, which means half of the base on this side. Well, the base is 616, so half of the base on this side is 8. And they're asking us for the radius of the semicircle. Let's call that x, for example. Okay, so there are several ways you could solve this. I am just going to try and use similar triangles here. Okay, so we know that this triangle I'm coloring in yellow, and this triangle I am coloring in green are similar because they both share this angle and a right angle. So that means that we can potentially set up a ratio of side lengths and solve an equation. So we know that we can basically figure out every single side of the isosceles triangle because we know that we have a right triangle with a base of 8 and a height of 15. And so if you remember your Pythagorean triples, then you'll realize that this other side here must be 17 because 8 squared plus 15 squared is 17 squared. So then the side ratio is 8 to 17 is equal to x to 15. So does that make sense to everybody? Okay. Okay, one person said no. So imagine we turned the little triangle around and we made, so the hypotenuse is 8, one of the side lengths is x. And we have our other triangle here. We have a hypotenuse of 17, a base of 8, and a height of 15. So because they're similar, this over this is equal to this over this. Okay, cool. So if we solve for x here, we get x is equal to 8 times 15 over 17, which is equal to 120 over 17, which is b. And that wraps up today's lesson. So thank you everybody for coming. And someone asks, could you have used estimation for the radius? Well, the radius is not really half the base. But you do know that half of the base is 8, and the hypotenuse of this right triangle is always going to be longer than the side lengths. So you already know that the radius has to be less than 8. So that basically narrows it down to only a few options. So yeah, you could have estimated kind of. Okay, so thank you everybody for coming. Um, do you guys next time, because we haven't finished all the geometry questions, so do you guys want to finish with geometry or move on to algebra? Okay, so most of you are saying finish geometry. So yeah, okay, that's what we're going to do next time, I guess. Okay, so thank you all for coming. Love you guys, and you can leave now. So have a great week, everybody, and see you next time. Oh yeah, combo is going to be the last approximately 2 weeks of this course. Okay, bye guys.